any message. We go for the structure of my short presentation, which is related to the demand of the digital twins in the mining market, the related trends, and some example of the digital twins. So first of all, the conception about digital twins is quite general. That's why it's important to understand which are the main issues which define a digital twin, because this is also valid for the mining industry. So first of all, a digital twin can be used for monitoring, diagnostics, and prognostics of a machine or a process. And with this, the benefit from the digital twin implementation and use is the optimization of the performance and utilization of the respective machine or of the process. Second, sensory data can be combined with historical data and, very important, with human expertise from site, as well as with the simulation learning. The benefit out of this is an improved forecast ability, an improved prognostics. And third, complex prognostics and state-of-the-art maintenance platforms can use digital twins in order to understand the root causes and hence to improve the productivity. That's why I used to say digital twins are a very good leverage to make the operators feel the pulse of the processes, feel the pulse of their mining site. So the next slide, please. Exactly. Now, there is an undoubtful demand for digital twins in the mining industry already. I picked up here only two examples. One is on the left side from Anglo-American, is one way to expect outputs from digital twin. It's a digital twin of a machine. It can be a compressor, it can be a mill, it can be a conveyor or whatever. And the second example on the right side is an example from Codelco. It's an inquiry. It's also related to Expande. We have seen it already in the previous presentation and discussion. So it's about the digital twin for a conveyor belt conveyor line. So basically, what I wanted to sketch with this pyramid here, digital twin is a solution which can be focused on each and every level of the mining company, be it machines, a mill, a conveyor, a crusher, be it a process, for example, the transportation process, or being a whole location, a mining site, or even the whole company, which includes more mining sites, more locations. And with this, I'll skip to the next slide to show only two trends related to the digital twins, which are considered today to be valid also for the mining industry. First of all, the key component of digital twin is a simulation tool, which has the goal to capture the product, the machine, or the process physical behavior. And the trend is simulations are expected to use more and more artificial intelligence technology. So the first trend which I would like to stress here is that the digital twins integrate simulation and more artificial intelligence technology. And with this, we switch to the second slide, to the second trend, which means the decisions supported by digital twins will be increasingly trusted in the mining industry as well. So I picked up a straightforward example. Let's think about the navigation systems we all use in our cars. So they are based on digital technologies and they are trustful. We trust them because they are convenient and more reliable, more trusted than, for example, a local person might be. So the same way, the digital twin and the simulation models are gaining trust also in the mining industry, which means we have an increasing trend to trust the simulations, to trust the digital twins also in the mining industry. There is an important step up front in order to trust such a solution, a digital twin, which is the validation. This is the accurate comparison of the results from the digital twin with the measurements from site. If this comparison is accurate, then we say the digital twin is validated and it can be trusted. So the second trend, the digital twins will be more and more trusted in the mining industry. With this, the companies that implement a digital twin today, they have a competitive advantage with respect to the others which come a little bit or later on. With this, we switch to the next slide, to the examples. As I promised in the beginning, I will shortly share with you some examples of digital twin for a machine, for example, for a SEG mill, for a belt conveyor, and also for a wagon tippler, and for a whole process, for a transportation process. For each of these is valid that basically the digital twin is based on the real machine or process, on the real world. It takes inputs from the real world and it optimizes the performance and utilization of the machine. It improves the outcome of the prognostics and it finds root causes of issues, of problems in order to improve the productivity. Let's see on the next slide, please, the first example. Perfect. Digital twin of a SEG mill. We have here the main functionalities. So, upfront detection of abnormal operation, support for early counteractions in case of problems, root cause identification with artificial intelligence, which is trained on real features, and prediction ability, which is enriched with local experience, with mill operators' experience in this case. And because this might be a little bit general, I step down a little bit, a small deep dive on the next slide. So where I specify, for example, upfront detection of abnormal operation related to the motor winding temperature, to the temperature of the winding of the motor driving the mill. Support for early actions, for example, related to mill vibrations. If the foundation vibrations increase over time, there is need for action. And early information about this is crucial to avoid unplanned shutdowns. Root cause identification. What we do is we train artificial intelligence models on real failures, which means the models, the functionality incorporates experience related to the respective failures. And with this, if this kind of issues appear, the model, the artificial intelligence model, detects it in a very early stage. And this gives the possibility to the mill operator to prepare himself for the coming up problem. And with this, to have savings because he can avoid an unplanned shutdown. And of course, related to the prediction ability, to the maintenance status, the real maintenance status of the mill and of the key components, I would stress here only the fact that we save in our digital twins the experience of the mill operator. And with this, we have a solution. We have a digital twin, which is not general, but it's tailored to the respective machine or process. In this case, it's tailored to the SAG mill. And on the next slide, the concrete example related to the return of investment, because we often receive from potential users of our digital twin solutions the question, okay, why should I, as mill operator, for example, why should I pay for this digital twin? What is the benefit out of it? And the question is reasonable, the question is normal. And here is one example of the answer. As I already mentioned, we say, okay, we have incorporated in the functionality trains, models which are trained on real failures. For example, an undetected increased mill bearing pads temperature. So here, for example, in the mill bearing below, there are these pads, and if the temperature there increases, then the lubrication process of the bearing is not okay anymore. The effect, if this gets worse, then the automation system of the mill generate a start permit condition, because this is specified by the mill producer. And if the start condition has been generated, then the mill cannot be started for 1 hour, because this is the time which is prescribed by the mill manufacturer in order to let the mill bearing pad temperature get again down. So 1 hour of production, you know, of course, it's around something like 130, 140,000 euro, at least, depending on the mine size. So this is one example. The second example is related to the mill seal grease cycle, which, if it's not successful, there are several attempts to improve it, because the mill builder prescribes this. And if no improvement is done, then it's again the mill automation which generates a mill shutdown. And such a mill shutdown requires afterwards 6 hours till the mill might be started again. This is again prescribed by the mill manufacturer in the manual, which means this is a saving, or this would be a loss in this real situation, which has been sometime a real failure. This is a loss of more than 800,000 euro. So only with these examples that I shared here, we can see a possible answer to the question, why should I, as mill operator, pay for a digital twin of my mill? Then the clear answer is because only based on these 3 possible real failures, they happen sometime to somebody. Only based on this, you as mill operator can save more than 1 million euro coming up as losses from unplanned still stands of the mill. The second example on the next slide, please. It's the example of the belt conveyor digital twin, which again incorporates a simulation model. It's validated, and it's even going real time during the operation in the next implementation phase. So as I already mentioned, this kind of model can be really trusted because it has capabilities to investigate the various effects of eventual changes on mechanics and on the belt, and because it can be used in order to understand upfront virtually various issues related to commissioning, modernization, and so on. So there are savings through shortened activities on site. So this is an example how a digital twin can contribute to improved activities, either shorter commissioning time or better understanding in case of modernization issues of the respective belt conveyor, and with this avoiding failures if the modernization activities have not been designed accurately. And on the next slide, only shortly, another aspect, with a digital twin, we can evaluate a failure which happened in the past, and this failure can be understood, and with this, actions can be taken so that similar failures do not happen in the future anymore. So, for example, here we present to you an example, a fictive example, where the main root cause was for a belt conveyor that the bulk material stocked in the discharge area of the conveyor. So bulk material got together and stuck in the discharge area. The effect was that the belt has been braked and finally blocked at that position. However, the drive station from the other end continued operation. It pulled the belt, and at a certain moment, the belt has been thrown out from the tensioning station, and then, of course, the drive has been stopped, but the effect of the belt pulled out from the tensioning station can be seen here. The belt has been deformed, the material from the belt has been thrown aside, the idlers on that area were damaged, and you know better than me what this means for the operations. And now the example related to the next application, which is the wagon unloading operation. So digital twin, which analyzes the difference between the specified performance and the real performance. For example, this installation, this wagon tippler should unload 25 wagons per hour. Instead, it really unloads only 18 to 20 wagons per hour. A cycle for a wagon upload should take 144 seconds according to the spec, and it really takes 180 seconds, so 30% longer time. And the hydraulic system valves, which help these clamps to raise the wagon and unload it, they are very often unplanned to be serviced. And with this, the hydraulic system manufacturer is something like 750 kilometers, and there are many unplanned visits on site. We pilot this since more than 1 year at one customer, and according to his statement, we contribute to an improvement of the productivity of roughly 20%, and translated into the sustainability language, this means more than 10 tons saved CO2 expansion in the environment. So we have also here artificial intelligence, which evaluate the pressure in the various clamps. This, what we see here with red as example, these are the anomalies, the abnormal operating valves, and this is all information upfront before the respective valve gets damaged, so that the operator of the wagon tippler in this case can prepare himself and can plan accordingly the service activities. The next slide is the last example as digital twin. As I promised, it's related to a whole process, from pit to stockyard in this case. So we model with a digital twin solution the whole material flow from pit, from loading the respective mining trucks, transporting it to load the material, the bulk material on the conveyor line. The trucks unload the material into 1 or 2 crushers, first of all, and from there, the material goes on the conveyor line, which is sketched here, it's pictured here, and after, 30 kilometers of conveyor line, the material arrives on the stockyard. Now, of course, to optimize this whole transportation process from pit to stockyard, it's not enough to optimize punctually one of the 4 conveyor belts or 1 crusher or whatever, because this is one optimum, but we need to understand which is the optimum of the whole process. And this is what we do with a so-called digital twin of the transportation process. We have a lot of functionalities inside. Some of them are sketched here below the slide. And this is basically the last example that I wanted to share with you. A very good one, which is very well received by the operator of the respective site. And now to the last slide, please, which is related to a short wrap-up to keep up with the time. So it's a clear fact that the demand for digital twins in mining is here. It's undoubtful, be it for machines, be it for processes, and it has the goal to optimize the performance and the utilization of the respective machines or processes. With a digital twin solution implemented on site, the real data, the sensors data, are combined with the history of the respective application, process, or machine, and for all are combined with simulation, but for all with the human expertise, which means through the implementation of a digital twin, we secure the very valuable experience of the people we have on site, of the operation people that know the respective site, machine, process since years or decades. We all know the problem, the challenge. Good people sometimes retire or sometimes they leave for other companies, for other challenges. And to secure the experience they have is a crucial leverage to secure in the end the productivity of the mining site. And this is where the digital twin solutions help very, very strongly. And last but not least, as I showed you one example, the digital twin solutions, they crucially contribute to sustainability through improving the productivity, reducing the environmental footprint of the respective site, application, or process, optimize business trips with this, minimizing the risks of our personal teams for servicing or for whatever activities on site. Less travel, less travels the people do, the less the risk they have on the way. We know that all. And with this, thank you very much. Looking forward for your questions or discussion. We get now the last slide as promised within the agreed time, hopefully.
Thank you very much. Un aplauso para Dan, por favor.
Let's give an applause to Dan. Gracias por tu presentación, muy interesante respecto a los gemelos digitales. Por favor, permanece en línea para que tengamos después el panel con la presentación. I'm going to ask